chapter 19 in the lecture outline. It corresponds to chapter 19, I believe, in the Ebbings 9th and 10th edition, electrochemistry. This is a specialty topic. When we finished our oxidation reduction and thermodynamics lectures, you have completed the survey course, fundamentally. You have in your toolbox all the necessary equipment now to work with any future subjects. Those future subjects are classified as specialty topics. You have, of course, electrochemistry, which we're about to start, nuclear chemistry. That's a little different in terms of nuclear considerations. But then you go into metallurgy, and then you go into formulation chemistry, biochemistry, organic chemistry, analytical chemistry, and just on and on and on, to many, many fields of chemistry, and all of them are based upon the survey type items that I've tried to share with you over the semester up to this point. Well, electrochemistry is the study of chemical electricity. An electric charge flow can be two types, metallic charge flow and solution phase charge flow. Well, electrochemistry, for the most part, is based upon solution phase charge flow. In the study of electrochemistry, there are two parts. There's electrolysis and galvanic process. Electrolysis differs from the galvanic process in that it is a non-spontaneous chemistry or non-spontaneous process. That is, delta G is greater than 0 for the process, and indicates that energy is required to move those reactions forward or make the chemistry work. So you have in the electrolysis a electrical energy generating chemical reactions. That's what I'm looking for. For whatever application that you're interested in. Now, on the other side of this coin is galvanic process, and that is spontaneous. With the delta G being less than 0, and these are chemical reactions that cause electric flow or flow of charge. That is, chemical reactions yield electrical energy. Now, as a spontaneous process, this is somewhat like rolling downhill on its own. So if you combine the half reactions in the proper way, they will give you a constant flow of electric charge. Flashlight batteries, car batteries, on and on are the examples of galvanics. Refining of metals, electroplating, copper plating, gold plating, okay, silver plating, is examples of the electrolysis process. Okay? Now, in the study of these, what we're going to do is we're going to look at what we call the cell structure, the chemistry of what's going on in these, a lot of terminology in the processes and some analyticals that associates with each one of these concepts. So we begin with electrolysis. And the electrolytic cell. It consists, if you will, of a battery jar. And in that battery jar, a salt solution or an ionic type solution, typically a salt solution. So that, of course, the issue is, say, A, B will ionize to cations and anions. So you have this collection of ions floating around in solution. Then there is in the solution a pair of what we call inert electrodes, and in the case that I will be discussing, these will be graphite electrodes. The circuit in the process is completed by attaching by wire the electrodes to a battery. The short symbology, short side, is the plus, and the long side is the negative of the symbology. Now, what happens if you connect these is this electrode, put a hold on that. I messed this up. I'm giving you the wrong. Just wanted to be sure before I went too deep into it. Okay. So what happens is the charge on this electrode becomes positive, entire electrode. And over here we have this electrode certainly being negative. Now, once that has been connected, keep in mind we have cations and anions in the solution, right there. And then these are attracted to the electrodes, opposites attract. That is, we find the cations being attracted to the electrode over here. I am having a senior moment here. Okay, I'll show you. Go ahead and finish this out. A goes over here. A plus will go to the negative pole and gain an electron and become neutralized. I know why I'm thinking of the galvanic process, trying to do electrolysis. Never mind. Okay. All right. B then migrates over here and delivers its extra electron into that electrode and undergoes oxidation. So B would deliver B minus, or deliver its electron and become B plus, or B0 minus I'll catch up in a minute, guys. Hang on. Okay, the point here is some terminology in the reduction and oxidation. When we look at this structure, when we look at the reduction side of this, we call that electrode the cathode. And when we look at the oxidation side of this, it is the anode. The names of the electrodes are defined in terms of the chemistry. That is, a cathode would always be assigned and related to the reduction process. And the oxidation side, or the anode, is always the oxidation. When you add these two together, you have a net reaction which defines the net reaction of electrolysis. Okay. Now that's the fundamental as far as terminology. Now you have two types of electrolysis. One, you have melt electrolysis, and two, you have aqueous electrolysis. Salts can be melted in large quantities, and in the process of melting, this frees up the ions to float around randomly, and if you put electrodes in there with the ions, they will undergo oxidation and reduction. We'll start with the melt electrolysis of sodium chloride. And again, what we want to do is draw our electrolytic cell, and we have sodium ions and chloride ions, say, in solution. And this time I'm going to hook this thing up. Here's an electrode. You know, I'm thinking that short side is, matter of fact, the negative side, and that's what's throwing me. I think I've got my poles backwards on the symbology, but that's neither here nor there. So if this one's negative, this one's positive, the process then proceeds because the electrodes will attract the oppositely charged salts. Yeah, I can't stand that. I've got to go back up here, change these. This should be a negative, and making all that negative. So now I'm going to make that just a second. I've got to fix this. I can't stand that. All right. It'll work now. I got to get my my brain warmed up too. Anyway, chloride will migrate into the positive electrode, and sodium will migrate into the negative electrode. And of course, the sodium will gain an electron and go to sodium metal at that electrode, and chloride right here goes to its basic standard state. Now, all of these reductions and oxidations produce basic standard states. Cl2 would be the basic standard state of chlorine, and it undergoes oxidation, and we have to have two of those. So to balance this, we have to double the first reaction as shown, and then add them together to get the net cell reaction. And so that would be 2 sodium ions plus 2 chloride ions will go to 2 sodium metal solid plus Cl2 gas, which is the net cell reaction right here. And that's pretty easy to deal with when you're working with melt systems. You just melt it and stick the electrodes in, the oxidation reduction begins to take place. The problem is when you start doing aqueous electrolysis. Aqueous electrolysis, or in aqueous electrolysis, there is a competition between the oxidation reduction of water as well as oxidation reduction of the ions from the salt. And there are two ways to define how this occurs. One, by simple experimental observation, and others, if you've got an oxidation potential table, you can generally tell which one will dominate, okay? So the way we do this, now everything will be following the same kind of cell design, but I'm not going to draw out a cell. This time I'm going to make a T-table like this, and on one side I'm going to make the cathode on the other side oxidation, the anode. So this would be oxidation. Two reactions. If we work with, say, potassium bromide in aqueous medium, like this, the potassium will undergo reduction and bromide will undergo oxidation. So we'll go ahead and put those two in. Potassium, aqueous, plus an electron goes to potassium, basic standard state, if it occurs. And the bromide undergoes oxidation to bromine, it's liquid form, plus a couple of electrons like that. You don't have to double, you don't have to add them together or anything. Now this is what the salt ions potentially do. But they're in competition with water reduction and water oxidation. Water reduction reaction is this. Where water picks up a couple of electrons and produces hydrogen gas and hydroxide. Oxidation of water produces O2 plus 4 acids plus 4 electrons. Those are the half reactions. And you can see these on the reduction potential table. If you pull out enough. Scan in and try to find these. It's kind of small right now. I can find water for you. Minus 0.84. There's the reduction reaction of water, and the oxidation is 1.23 down here, way down here. This is the oxidation reaction. So you kind of want to keep those handy as we go through this, because we'll be needing the numbers minus 0.83 and 1.23 in just a moment. So I would recommend, like I say, just marking those positions. Now, if you hook this up into an electrolytic cell, what you would have, this is aqueous. Of course, you have potassium ions and bromide ions in your electrolytic cell hooked up to your battery, as shown here, minus, plus, and the potassiums would theoretically move to that electrode, bromide move to that electrode, and you would get the first reaction. But how do you know it is occurring or is not occurring? Well, one of the things you would observe at the negative electrode, the reduction side, the cathode, is no metal potassium is being formed. But what you would see is a large number of bubbles being generated right here. You would see hydrogen gas being generated, and if you tested it with litmus, you would find out it was basic at that electrode. So you're not only generating hydrogen, but you're also testing it to be basic. So what I'm saying is the second reaction here is the dominant reaction at that electrode. That is at the cathode. On the other side over here, what you would see is a cloud of purple liquid being formed over here, and that is the color of bromine being formed. So from an experimental observation standpoint, the dominant reactions are the bromine reactions and the water reactions. So when you construct the net cell reaction, you add those two reactions together to get your net cell reaction in this one case. And the electrons drop out, and 2Br minus plus 2H2Os go to 2H2 plus OH minus plus Br2 in liquid. So this is your net cell reaction. This is your cathode dominant reaction. And this is your anode dominant reaction. Like that. And all of that was determined exclusively from experimental observation. Like that. Now, there's another way to deal with this in terms of reduction potentials. In the table, you see some numbers over here, and these are called electrode potentials, reduction potentials. So what I want you to do is over here on the outside of these, I want you to write a minus 2.924 volts, and water is a minus 0.84 volts right here, and over here bromine is a plus 1.07 volts, and the water is 1.23 volts. This you have to memorize. The more negative anode, the more negative reduction potential at the anode is the dominant reaction. Or you might say the more negative potential is dominant. Over here, you see the more positive potential is dominant at the cathode. For me to remember those, what I use is the acronym PC, like it's a computer or something. Positive is at the cathode, and the NO, negative, oxidation. Okay, negative is oxidation. Now what you use to memorize that's your business, but that's how I essentially do it. Now, we've got 3 more examples to go through like this. We set them up all the same way, and you come to and the questions on the exam, which of the following reactions of this electrolysis is the dominant reactions at the cathode or the anode? That's how it comes to you. And so it's very important that you develop some sort of memory device to separate these two. You're not going to be able to set up the experiment on the exam. Okay. The second one we want to look at is copper sulfate. Okay. And it'll go a lot faster now. Copper sulfate ionizes the copper plus 2 plus your sulfate like that. So make your T table across like that. And you want, I like oxidation. Oh no, I like the reduction come first because I want to do the metal first. So that's the cathode. And then oxidation anode. Okay, so when we talk about the copper reduction, it's gain 2 electrons, and we go to copper metal, and the SO4 minus oxidation goes S2O8 minus 2 to plus 2 electrons. You can look that up on the sheet if you like. Then, of course, the water reduction is still the same. H2O plus 2 electrons goes to 2H2 gas plus hydroxide. Oxidation is 2H2O goes to O2 plus 4H plus 4 electrons. Then you put in your reduction potentials. The copper is a minus 0.34 volts, and water is still minus 0.83 volts. Your sulfate is 2.01 volts plus, and the water still 1.23 volts. So it's NO and PC that dominate. So in here, look at this. In this case, the more dominant reaction is the copper. And over here, the more negative one is the dominant reaction. So we have the metal on the reduction side. So in the previous example, you saw the dominant reaction was the water, not the metal, and the reduction side. Here on the reduction side, because of the reduction potentials being more positive, we see the metal is the dominant reaction. So you'd add those two reactions together, and you'd get the net cell reaction. So this goes a lot faster now that I've gotten through the one. You've seen at least that first one. You can divide through by 2 if you want to, or multiply the first one by 2. 2, 4, 2. So you got 2 coppers plus 2 plus 2 H2Os go to 2 copper. Reduced form plus O2 plus 4 acids. And that looks like the net cell reaction. So you divide through by 2 and you'd have a half mole of oxygen, but that's up to you. Depends on what the listing is on the exam. Okay, so that was copper sulfate. What about copper bromide? Okay, let's do copper bromide going to copper plus 2 plus bromide. And that should be a 2 there. Like that. So again, you set up your metal against the non-metal, left to right, or your reduction side goes to your oxidation side. And let me move this up here. Maybe we can get a little more room. Try to clean it up a little bit here. See if I can. I don't need that much space. Okay. Square it up a little bit so it doesn't look like we're getting vertigo. And so I like to work with the metal first, so that's going to undergo reduction, cathode, oxidation, anode. So we've got copper undergoing 2 electrons going to copper solid, and then 2 bromides going to bromine plus a couple of electrons. Then we have 2 H2O plus a couple of electrons goes to 2 H2 plus OH minus 1, 2, 2 is 4. Oh, that should not have a 2 in front of it. Sorry about that. I'm just not all here today. Should be the 2 should be on the hydroxide. If I did that on let me see if yeah, I did that. This is not correct here. I'll correct that. And thank goodness it wasn't a dominant reaction in that one. But at any rate, oxidation to 2H2O goes to O2 plus 4 plus 4 electrons, 1.23 volts. You get to where you can get these memorized, minus 0.83 volts. Copper is, I don't have yeah, minus 0.34 volts, and bromine 1.07. Okay, 7 volts. What do you need?
Where are you getting the negative from? Because on the chart, where are you getting the negative 0.34 from?
Oh, I'm sorry.
Because on the chart it says 0.34.
From the electrode, from this table, did you get one of these?
Yeah.
Okay, we got water and water. Those have those numbers, and you kind of have to hunt for the metals and non-metals, like copper. And kind of copper is a minus 3.4, so you kind of scan down here and you find copper minus. Well, let's see. Yeah. Well, that's not the right copper. May not even be on this. Well, it ought to be on here. I copied it right out of the textbook. Copper gains 2 electrodes, goes to, here it is, plus 3.4.
Yeah.
Oh, okay. Okay. Plus 3.4. Thank you. And bromine, just to check it, bromine is 1.07. So, yeah, that one's okay. Sorry about that. Thank you, sir. Appreciate that. Okay, well, again, it's a PCNO issue where the more positive, which of course is the copper one in this case, and the more negative one would be here. So both salt ions undergo the oxidation reduction in this case. So your net reaction would be adding those two together. And copper plus 2 bromides goes to copper plus Br2. Like that. So you see how in different salts, the ions, some ions dominate, but water dominates in some cases. And here, in the next example, and I do all 4 of these to show you these issues, sodium or potassium sulfate. Do potassium sulfate. Here, neither one of the salt ions dominates. Both dominate by the water half reactions. So, again, this would be a sodium, let's do potassium. I think I got the numbers up here. Potassium sulfate ionizes to a couple of potassiums and your sulfate like that. And so it would be potassium and sulfate potential oxidations reductions in this case. And bring it on up here. That. Square it up. So I think you're getting the gist of the flow of what I'm trying to do here is pick out the dominant reactions based upon either experimental process or if you have the electrode potentials, who's more negative, who's more positive. But this is a reduction side, cathode. And here we have potassium plus 1 electron goes to potassium. And so oxidation, anode, which is your SO4 minus 2 goes to S2O8 minus 2 plus a couple of electrons like that. And then you have H2O plus 2 electrons goes to H2 plus, see if I can get this right this time, OH minus, and then 2H2O goes to O2 plus 4H plus 4 electrons. So after a while, you get the way you know which ones are doing what. Okay.
On the reduction side, shouldn't it be
Pick up.
potassium?
What about?
2 potassium on the reduction side. Shouldn't there be 2 of the,
Let me stop this thing here. I'm not understanding your question. Okay, so let's look up the electrode potentials for potassium. And according to my sheet here, I've got a minus 2.92 volts. For the potassium and water is still minus 0.83 volts. And the sulfate is 2.01 volts. And the water is 1.23 volts. If I haven't misfired on that one. Yeah, that's a minus 9.29. That's correct. Okay. Survived at that time. So, PC and NO. Alright. So, the dominant reactions is the more positive reaction in this case would be this reaction this time. And the more dominant reaction would be the more negative reaction, and that would be not sulfate, it's going to be the other one. Did I write these down wrong? Sulfate is the more dominant reaction. More positive. Sulfate up here. 2.01. Oh.
Should be like S2O.
I see what I did. I looked at that. Yeah, I'm sorry. Today's just not my day. I saw the negative on there. So negative goes over here with that electron right there. Okay. The more negative is some days. So in this case, both water half reactions dominate, and you have 2 H2O plus a couple of electrons goes to H2 plus 2 H minus, and then you have I'm going to cut that one in half. I'm going to cut that one in half before I put it down here. So I'm going to say H2O goes to half mole of O2 plus 2H plus 2 electrons, like that. Now what I want you to see here is the electrons drop out, but what you'd have to do is you have to add those two together and then simplify like we did in the oxidation reduction simplification. And so you have 2 H2Os plus an H2O goes to half mole of O2. Clean that up a little bit. Half mole of O2 plus those go together to make 2 H2Os. Like that, which will cancel here and here. I forget my hydrogen in here. Yeah, plus H2. I'll throw it over here. Well, that leaves this, and this is your net half reaction right here. This is a classic way of doing laboratory preparation of hydrogen and oxygen, is to take a water, put 2 electrodes in it, and regardless of what the other reaction is, you can throw in some acid and initiate the reaction. But those are, when it runs, you'll see some inverted tubes. In many cases, you will watch this online if you like that, and they'll have this hooked into a system down here with a couple of electrodes in it, like that, and it'll send hydrogen to one side and oxygen to the other side, and you'll see the oxygen will come up to say here, and the hydrogen will come up to right there. So it's a classic method of making oxygen and hydrogen in the the laboratory. It also shows how water has a 2-to-1 reaction ratio in its simplest formula. Okay. The only thing left here is the analytical aspects of electrolytic cells. Why don't we take about a 15-minute break, and I'll start at 3:30 on that, and we'll go till we run out of steam. Okay. I need a break.